Welcome back. It's Monday. We're going to blitz remaining materials so that we can engage our Module 2 assessment soon, and I'm going to post the solution. The solution for this module will engage this device shown here. That's right, folks. Each of you, in one form or fashion, has a Wi-Fi router somewhere near you. And if it's not something you can control, or if you're in the dorms, what you can do is visit your home. You'll have till the end of the week to do this, okay? You can visit a friend's house. You can visit a relative's house, right? Who has one. And then you can engage the criteria for our solution using a loaner, so to speak, okay? If you need me to vouch for you and validate, yeah, this is legit, I can send a short email that you can show to your friend or family member, or maybe it's where you work and there's a supervisor that you work with and you have these things operating in your work environment, right? So let me know if that's an issue, but you'll see the solution for Module 2 posted. And essentially what we want you to do is to walk through some of the relevant points of interest with a Wi-Fi router, because as we stated in our previous session, it is not just one piece of network equipment. It is actually several all in one box. In fact, it's often referred to as an all-in-one by Cisco. They have business grade models they refer to as an all-in-one router, an all-in-one router. And they don't call it a Wi-Fi access point. They don't call it a Wi-Fi router. They call it an all-in-one. And that's a marketing thing. And they charge like 3 times as much as everybody else. Any questions about what we've just stated? Are there any questions about what we just stated? Okay. All right. So this particular part of the interface, I'm going to take the time to call out one more time, because this is the weirdness or mental wrinkle that throws many students. We refer to exit traffic and we use the term egress. Network egress is the route through which network traffic exits out of the local area network to the next network or internet. Any questions about that statement just now? Ironically, even though it is exit traffic, it hits the inside interface for the wide area network or internet port. Oftentimes on the back of a Wi-Fi router, it's colored differently and it's set apart intentionally. So you have 5 or 6 blue ports, and then you have a yellow port or an orange port or a red port. Does everybody understand what I'm talking about here?
Yeah.
Okay. All right. And when local network traffic is exiting, it first hits the inside interface for the WAN port or internet physical port. That inside interface possesses a, hang on just a second. Yep, sorry about that. The inside interface of the WAN port has the gateway address for the local area network, typically assigned the gateway address for the local area network. So if you're on a 192.168.0.0 internal private local network in your home, this inside interface would have 192.168.0.1 typically. Any questions about that remark? Going once. Can somebody unmute your mic and let me know you're alive? Any questions about this particular point of interest?
No questions.
Okay. So when you see references, you're connected to your Wi-Fi router like I am here. And I go to my command prompt and I run as administrator. And I type in ipconfig/all, and I look at my Wi-Fi router. I see my default gateway here. This is I have an ASUS Wi-Fi router. I'm not going to tell you what model because I don't want you to go out on the internet and then look up the default password and then hacks for that, because sometimes students in networking get playful. And I'm not, not disparaging anyone in our current class. I'm just trying to make I'm just trying to shed some humor in the midst of our holiday torture. And if I'm failing badly, don't hesitate to tell me so afterwards, but I'm trying to be lighthearted here. Okay, so the inside default gateway for my local Wi-Fi connection, the one I'm using to deliver the class with you now, is assigned to the inside internet. That's the inside private network. That is address translated into a public address. The public address is something that you see when you type in GRC shields up, right? So, or you look it up on network-tools, or I found to be more accurate lately, for some reason, GRC shields up is not always consistent with the output, the outside. And by the way, we're walking through these details now and explaining this because it's a matter that you're going to encounter for your solution for module 2, okay? So here is the public IP address of this connection, which is flowing through the public side, the public interface. So this is the private internal interface. 192.168 is a private internal address range. The IP address that you see on the outside of this router is what the internet service provider uses to assign to this same physical port. The outside interface is often called the ingress. It's called the ingress because inbound traffic flows through this physical port, and this ingress traffic or inbound traffic hits the external port, the external side of the physical port, right? And it also has a public IP address, right? So there's a translation between private and public that happens right here. We're going to talk quite a bit about network address translation. There are 3 flavors of that, and it's pretty interesting stuff. Any questions about that detail we just walked through? We can move faster and finish sooner if somebody says, yeah, no, something.
No.
Okay. All right, we're good. All right, just want to make sure we got everybody here. Looks like we lost someone. We'll keep moving. I want to go here just to double check. I may tweak the solution. We're going to find out in just a minute if I'm going to tweak the solution before I post it, because I may require you to do this and say, what is my IP address in the Google prompt? If the Google prompt address differs from the GRC shields up address, you'll need to call that out and basically submit both, right? In this case, 198.26 198.26. 208.84 is a Class C public IP address. And it's what my broadband VI connection provides to my router. Okay, so moving right along. Yes, it slices, it dices, it's an all-in-one device. It has a switch. So it has a switch here, and this is where the 192.168 connections present. Also, there's an interface that bridges out to the Wi-Fi. Even though the Wi-Fi acts like a hub, it's still the 192.168.0 range. Why am I telling you this? If somebody's connected to the Wi-Fi, they can see everything anybody is sending and receiving if they are connected to the Wi-Fi. However, if they are connected to the switch, people who are connected to the Wi-Fi cannot. Also, there's a feature on most Wi-Fi routers to turn up what's known as a guest Wi-Fi network, which is established on a different internal VLAN altogether. It's usually a 192.168.2 or a .10 or something else, right? And that helps with security. So there you have it. Any questions about what we shared there? We haven't talked much about a router, but a router as the gateway is going to route packets that have an IP address that says, hey, I want out. If it's got an IP address on the header of the packet, whether it's Wi-Fi packet or Ethernet packet, see, whether it's a Wi-Fi frame or an Ethernet frame, when you unload the payload of the frame and you look at the header of the IP packet, if that packet says, and that's what the router does, the router unloads it, it unpacks it, and then it says, hey, is this a 192.168.0? Yep, it stays here. Nope, it goes out. If it has anything different than the local area network, it's routed out. That's what a router does. A router makes decisions based on the address information, sender receiver, right? Source and destination is what we call it. And using the source and destination, it makes a decision, split-second decision. Is this here or does it go? And it uses the subnet mask to do this, okay? All right. So we need to talk about industry standards because they're always changing. And it turns out that last year, when I was finishing up this module with a class that came before you, this new thing called Wi-Fi 6 came out. Has anyone ever heard of Wi-Fi 6?
No.
No. Okay. Well, believe it or not, the AC fast as lightning wireless router that you may have purchased 2 or 3 years ago, they have a new standard called Wi-Fi 6, and it's supposed to be new and improved and delivers much greater bandwidth. The jury is still out on that yet. It all depends on your local environment and interference and so on. So don't go tossing your fancy Wi-Fi router if it's only a couple of years old. Do your homework, right? The difference may not matter at all, especially if you have a lot of obstacles in your environment and everybody's using the 2.4 gigahertz signal for Wi-Fi instead of the 5 gigahertz signal. And of course, there's 5G cellular service, right? So these things are always changing, right? Sometimes industry standards are not really standards for the industry. Not in the formal sense of a standard where they're ratified internationally by subject matter experts. In some cases, a group of industry companies come together and they just kind of do their own thing. And these are often called de facto standards. That means that it's a practice or convention of the industry, but it's not necessarily a formal standard that you would find as promulgated by the IEEE and the IETF, the Internet Working Engineering Task Force, right? So in any case, I want you to understand that your author makes a point of making fun of the fact that network standards quite often, well, depending on how they're written and depending on how the manufacturer implements them, may not be completely standard based on brand. You may not be shocked to know this, and there's probably very little that any of us could do if you purchase a device and it kind of plays nice with other network devices, but not. And sometimes bad industry leaders do crap like that. And I'm just speaking frankly here. They pull stunts like that so that you have to buy other devices with the same brand. Once you've already gone to the trouble of spending $200 or $300 on a certain brand of Wi-Fi router, the best way to make it work is to, oh, let me guess, buy bridges and extenders of the same brand. And then heaven forbid you buy a different brand and you have problems, they'll say, well, you'll have to call the other manufacturer to get that to work for you. It's a game. You need to be aware of how the game is played, and you need to understand the limitations of standards, right? So when we say that there's a practice that the industry does, and it's not formally ratified internationally as a standard by the IEEE, the ITE, or the ITU, or ANSI, or take your pick, all of the above, IETF, then it means that yeah, it's not really a standard. Now, how are standards ratified? I want to take a little more time yet to explain that to you. If I have a standard and let's see, RTF for latest RTF for 802.11. Okay, so 802.11 is one of the primary and major standards. And basically, RTCs request for comments, right? They send out a document and they ask people to comment. They ask people to comment, and then they have a conference, and then they vote. And these documents are called RTFs. RFCs. No. All right, let's take that back. RFCs. Hold on. RFCs. Sorry for that. I guess I need another cup of coffee. RFCs. All right, so here's an RFC, request for comment. They put out a standard, an industry leader puts out a standard. They're usually a member of a consortium like the IEEE. They host conferences. They deliberate on the standard. They determine whether or not it's an effective or appropriate standard. Then they vote on it internationally. And you can reference the RFC, the request for comment that went out originally. And it tells you who in the Internet Engineering Task Force requested the comments of their colleagues and peers about the IEEE 802.11 wireless transmission standard, right? And there's several variations of the 1.1 standard, right? And you see that this happened in 2015, so it's relatively current, you know? Just remember that that's how official standards start to become a reality. And it takes quite a long time. It's kind of like birthing an elephant or a baby. It takes a long time. Any questions about RFCs, not RTFs? So here you see a train wreck. Can everybody see the screen?
Yeah.
So in the early stages of the internet, there were industry leaders that had their own view of what TCP/IP was all about. And they actually had a model based on 4 layers in the early days of the internet, right? So you see application layer, host-to-host transport layer, internet layer, and network interface layer. They did not have a 7-layer international standard known as the OSI. And they also mapped a series of functional protocols to each layer. So Ethernet, token ring, frame relay, ATM are all different transport mechanisms, right, that operate on the network interface layer. Then the internet layer, you see ARP, IGMP, ICMP. This is where the IP layer takes up. And then here's TCP and UDP on the host-to-host transport layer. And then on the application layer, in the early days of the internet, they had Telnet, FTP, SMTP, which is used for email, DNS, which is used to help you find things by name or email people by name, RIP, which is a protocol used to automatically establish the routes from one router on a public network to another router on a public network, or it could be a very large internal network. It's kind of like DHCP, except for routers, where the routes between routers are determined automatically. SNMP has to do with management of the network, right? And yes, everybody had their own kind of model. This is a very frustrating thing. I want to check this link to make sure it's still working. There we go. There's another view of it. This shows that basically we had this mishmash. Now, here's where things get interesting. And this is very, very important. So what I want to do now is give everybody 30 seconds to take a break and then refocus on the screen. So 30 seconds. We'll hit the pause button and the mute button. Go. So have you ever been on a network where you notice the network equipment is really kind of old? It's old.
Yeah.
Yeah, yeah. And if it was made way back in the day, it was made with these models in mind. Put another way, you can have the 5-layer internet model that the industry leaders like to use, the people who create the networks and work the networks. They have 5 layers. The folks who started the whole thing up 35, 40 years ago, they had a simpler model, 4 layers. And now, of course, you have the international standard model. And here's where things get interesting. In order to troubleshoot properly, you have to be able to map those different models with each other. Sometimes when you're troubleshooting. Now, this is not in a textbook. What I'm sharing with you here comes from 25 years of IT experience as a certified systems engineer with Microsoft, okay? And what I'm telling you is that you can have all kinds of equipment from all kinds of manufacturers, and depending on how old it is, when you're troubleshooting, you're working with their reference material, their help, their online help, their support documentation, which is based on what? A 7-layer model? No, it's based on a 5-layer model. If it's really old, it's based on a 4-layer model. So what are we saying? You kind of have to logically translate between the layers in order to make sense of troubleshooting when you have a mixed bag of old and new networking equipment, okay? So how does that manifest? Oh, and by the way, in the early days of the internet, this is just a short list of all of the different protocols that were active. It's an expanded list of what's shown here. What you see here, this is just an expanded list of the same. So when you click those links and go in there, you know, in the early days of the internet, these are all of the juicy protocols that made the first generation of our internet operate on the application layer, on the transport layer, internet layer, and link layer. But when you come down further, what happens is that you have to be able to translate between protocols. Now, we may revisit this in the next module. In fact, I think that's where we're really going to get into the weeds with it. We're going to have in the next module a setup where you're going to see the 7-layer model next to the 4-layer model next to the 5-layer model. And we're going to give you scenarios where you have to kind of walk through it. You'll say, oh, well, there's, you know, a network software engineer that's working a solution with OSI model, and he's trying to solve a problem with the connectivity on layer 3, but the equipment manufacturer, they don't use that model. So what layer are they working with? We just want you to keep that in mind as we keep going through this review. The media access control protocol and ARP is where we want to spend the balance of our time. Mac is a, well, it's kind of a, we take it for granted. We take for granted how important a MAC address is. And I'm going to copy this value. And then I'm going to click this link. If you know the first characters of a MAC address, you can determine who the manufacturer is. So if I click that link, it takes me to the wireshark.org page where there's a lookup that tells you who is doing this MAC address. And you see what? This is an Apple system, right? So if I look at 68, now 68 Delta Bravo Charlie Alpha is not the only set of characters allocated for Apple. They could have other characters. I'm just saying. What happens is that there's often multiple sets of characters for a given manufacturer, depending on the size of the landscape for their products. And of course, Apple is huge. There's a lot of Apple products, network products, mobile devices that network with both 5G and, you know, IP networking. Any questions here? You should look at your MAC address in the instance here, and you can do this if you press Control C. The highlight disappears and it seems like it didn't actually copy that, but if you go to this address again, you blank it out. See, as long as you have an example that abides by the format shown, if I click find, now I'm dealing with an Intel component. It's made by Intel computers, my Wi-Fi. Okay, and you can do that right now. The thing to remember is that it's a 48-bit hexadecimal value. That doesn't mean that you have 48 characters here. In fact, each character represents 4 bits or a nibble. So together you have 8 bits and there are 6 pairs of those. What's 6 times 8, everyone? 48 bits.
48.
48. And if you want to see those bits, ones and zeros, you can use your handy dandy programming calculator, shift from scientific to programmer, and you can basically click on the hex and then type in D, which is actually, it represents a number in the hex system. D represents a number in the hex system. We'll talk more about that in our next module. When you click on that, DB, if I take DB, the ones and zeros for DB are 1101, 1011. For a hex pair, Delta Bravo. Any questions? If I were to use this in an IP address for an octet, it would be a 219 dot something, right? Okay, let's talk about ARP. When you first connect to a wireless or an Ethernet broadcast domain, whenever you first connect to a broadcast domain, your machine starts to sound off. It transmits a special type of announcement. It's called a gratuitous ARP. A gratuitous ARP is the first, gratuitous means free. It belches out ones and zeros. It basically says in ones and zeros, hey, I'm here. It's a greeting on the entire network. It just says, when you connect, it says, hello, that's me. And then other equipment on that network can respond, right? In particular, the response we're looking for with the ARP broadcast is a response that will assign an IP address. The whole point of barking with ARP, just think of barking with ARP. I'm trying to deprocess here. I know it's a poor attempt at humor, but ARP, 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 right? Sounds like a dog, right? Barking, ARP. We're broadcasting. What we want to do is say, I'm here, and the MAC ID is included in that ARP, and the MAC ID is provided through that gratuitous ARP, and the response back is an opportunity to be assigned a lease for an IP address. Now, does everybody understand what a lease is? Do you own something if it's leased?
No, you're just borrowing and you're making some sort of payment on it.
You're just borrowing it. That's right. You're just borrowing it. An IP address lease is often assigned by a DHCP server, a dynamic host control protocol server. And it's the DHCP server that's listening for the gratuitous ARP. Now, the cool thing is that at the edge of that network, that broadcast domain, you can have a router that likes to relay those ARP announcements, the gratuitous ARP announcements. What am I saying? It's called a DHCP helper service. Now, why should you care? I mean, really, truly, why would that be a big thing? Well, it just so happens that networks were very limited geographically until somebody figured out, okay, here's a device that connects. It says, I'm here, but what if our DHCP server is on the other end of the campus? It's 5 buildings away, and there are different network addresses in between, network address ranges in between. How the hell does that DHCP server answer to this local client that barks out in the local pond? The answer is DHCP helper. You can send and receive data on layer 2 with a MAC address, and you don't even need an IP address to start doing that. That's kind of weird, but the reality is on the broadcast domain, you don't need an IP network address in order to be able to send and receive data. In fact, there are many other protocols besides IP. This is where the University of Michigan cheat sheet comes in. And then here we talk about broadband. And when we're talking about broadband, we're going to be talking about, well, we're going to be talking about via modems on Wednesday. So what are we saying? We're going to be talking about your broadband service, and we're going to give you some insights that will turn you into a rock star when it comes to troubleshooting your internet connection with your internet service provider. The good news is, if you get some crazy static from them, and I know this hasn't happened to anyone, but have you ever called your internet service provider and said, hey, I have a problem here, and they have you go through a bunch of like checklist questions with them, and then they give you some like canned answer, and it really doesn't solve your problem? Has anyone ever experienced something like that?
You mean like when they tell you to plug it out and wait 10 seconds and it doesn't fix anything?
That would be a great example. They have a checklist they have to walk through. What we're going to talk about on Wednesday is the checklist and what you can do to get more from your support. Okay? So stay tuned. We'll start with this section on Wednesday. Any questions before we clear our session?